Okay, let's start. A very good afternoon, everyone. Welcome to this problem solving session. It's our week 5, and today we'll be discussing about stability analysis, which we have discussed in the last week, and one very important topic, which is very important for this course, from this course point of view, at the same time, from your exam point of view. Uh, Semester exams or GATE or NPTEL final exam. It's a very important topic. That's Routh-Hurwitz stability criteria, or like how do we solve stability problems using Routh-Hurwitz criteria. As I have been telling you that I have also taken the TAs for another course in the previous semester, that is control engineering, and the videos for which you might get on my channel, which is already shared with you. So in that channel, you'll find week 4 is Routh-Hurwitz criteria, and that is discussed in detail. And I have in that video, I have started from the very basic, from very basic questions to very advanced, complex questions. So do check out that. Now, today's lecture, in this lecture, I will keep, because this is an easy topic, everybody, easy but very important, but and most people are able to grasp this concept, right? And you must have seen the assignment questions. They're also not that difficult. So one thing, I repeat that if you're coming to this video lecture, this problem solving session, I would assume that you have already gone through the assignments. You have gone through the video lectures of the professor, and you have also attempted questions, or you know what are the questions, what like how to solve them. At least you have some idea. Then and only this will be fruitful. So today I'll be focusing on some very good questions. I assume that you have a basic understanding of Routh-Hurwitz criteria and other stability problems, and you have already gone through some basic problems. So we will solve some very good questions, which will be helpful to you. Okay. So by the time others join, I'll just recap some important concepts before we begin the problems. So let's start. So basically what we are going to study today is stability. So till now, what do we know? We know we're given a closed loop transfer function. We are given a closed loop transfer function. From this closed loop transfer function, we find the characteristic equation of this closed loop transfer function. And from this characteristic equation, we solve this and find the roots, which we also called as poles. Perfect. And based on these poles, we characterize whether my system is stable, marginally stable, or unstable. Perfect. So if these poles, if they lie in left half plane, if they lie in left half plane of the complex plane, so I'll just make the complex plane here. This is my sigma and this is j omega. So basically this pole, let's assume I'm denoting it as S, it will be something like this, S plus j omega. It has a real part, at the same time it has a complex part, and which we are plotting here. So this is right half plane and this is left half plane. So if my poles, if they lie in the left half plane strictly, so if they strictly lie here, all the poles, if all the poles they lie in left half plane, then my system is stable. right? So it doesn't matter. So even if the poles are repeated, so for example, my poles are like this, they're repeated, but they are, as long as they are in the left half plane, the system is stable. Poles can be like this, poles can be like this, complex and repeated. Poles can be like this as well. As long as they are in the left half plane, the system is stable. Now, if any of the poles, sigma j omega, if any of the poles is in the right half plane, any one, then my system becomes unstable. I don't care then. Where are the other poles? If any of my poles is in RHP, so my system is unstable. Perfect. Now what is left? What if my poles are on the imaginary axis? What if my poles are on the imaginary axis? So if my poles are on the imaginary axis like this, my poles are on the imaginary axis, sigma j omega. Let's assume my poles are something like this. There are two poles on the imaginary axis, or there is one pole. So if poles are on the imaginary axis, but they are either simple, means I have only one pole, or they are not repeated. So they are simple. If poles are simple and or I'll write not repeated. They can be anywhere on this imaginary axis, then your system is marginally stable, right? So even if let's assume you have five poles, three among them are in the left half plane and two on the imaginary axis, because whenever poles will be on the imaginary axis, except at zero, there will be two. At least there will be two. So if the pole is at zero, that's fine. The system will be marginally stable for sure. But if other than zero, whenever you have poles on the imaginary axis, there will always be two, because complex poles always occur in pairs. Perfect. So whenever you have poles on the imaginary axis and they are not repeated, then the system is marginally stable. But if you have poles on the imaginary axis, but they are repeated. Even if you have two poles on the origin, but repeated, or you have anywhere on the imaginary axis, but repeated, that makes my system unstable. I have told you in this before as well. So just remember this point. This is very, very important when we are solving Routh-Hurwitz criteria or questions based on RH criteria, right? So it means if I have poles or roots of the characteristic equation on the imaginary axis, the system will be marginally stable. But it can be unstable as well if the poles are repeated on zero or anywhere on the imaginary axis. If they are repeated, the system can be unstable. Okay, so your system can be unstable if your poles are on the RHP, right half plane, or on the imaginary axis but repeated. Perfect. Now let's solve question. That's it. That's all needed. So just remember this point because we'll be using it frequently. You'll see it. So our question number one is we have consider a polynomial in S given as, so we are given a polynomial P of S given as 3s4 plus 2s cubed plus 4s square plus 14s plus 23. This is the polynomial given, and the question is how many roots of this polynomial equation will lie on the right half plane. Okay? The question is how many poles of, not poles, how many roots of P of S equal to 0 will lie will lie on the right half plane, RHP. So first question, that's why I'm writing. Okay, so now see, if you have a second order system, it's easy to find the roots. You have quadratic formula, you have other methods, splitting the middle term, etc., etc. Or you can use some other methods. But so basically for this question, you have to solve the equation, find the roots. That's it. But there are different ways of solving it, of finding the roots. We can reduce it to second order or third order and then solve it. So there are many ways, but we will solve it based on RH criteria, right? We will use Routh-Hurwitz criteria and we will understand RH criteria based on this example. So what is RH criteria? In RH criteria, what we do, we find the roots of characteristic equation and we basically find the location, right? So we basically find the location of the roots. We do not find exactly the roots, but this RH criteria gives us the location of the roots. So we know if the roots are in the right half plane, then my system is unstable. So I can easily decide stability based on RH criteria because in stability I do not need the pole exactly. I just need the location of the pole. If a pole is in the LHP on the LHP, my system is stable. Otherwise, it's unstable if it is in the on the RHP or it's repeated but on the imaginary axis. So we will understand this RH criteria based on this example. So what we do, so this is just the polynomial, but when we are solving transfer function based questions, then this will be your characteristic equation. So assume this is your characteristic equation, right? Let's assume for this question, this is your characteristic equation because when you solve, you basically solve the characteristic equation, you find the roots of characteristic equation. So if we are asked to find whether the system is stable or unstable, you just solve the characteristic equation. But for this time, for the time being, just imagine this is a polynomial given, but you can imagine this to be a characteristic equation because from other questions onwards, we will be using only the characteristic equation. So you are given this polynomial P of S. So what you do, you make an array. The highest power is 4. Okay. So what you do, you make an array like this. You write S4, okay, then S3, S2, S1, and S0. Okay. Then you just populate the first two rows. Sorry, yes, the first two rows. Your first row is the coefficient of x S4. So I'll write the coefficient of S4 here. Then I will leave one. I'll write the coefficient, like I'll write odd, even coefficients first, and then the odd coefficients for this problem. If this would have been S3 here on the, like if there would have been S3, then I would write odd coefficients first, then even coefficients. So this will be 3, and then this will be 4, and this will be 23. So I wrote even coefficients first, then I will write odd coefficients. This will be 2, this will be 14. 0. There is no coefficient. Okay, or basically you have to write alternate coefficients. Now, how to populate other rows? How to populate other rows, S square, S1, and S3? Just listen, remember. What you have to do, you have to multiply 2 with 4. So I'll write here 2 into 4. Then this into this minus 14 into 3. Make sure you have calculator with you. Then divided by this term will be 2. Okay. Similarly, this was first element of S2. Now second element again, second element, this into this, then this into this, not this, sorry. And then divided by the first term. Okay, so this will be, I'll write it here, 2 into 23 divided by minus 0, 0 into 3 is 0, divided by 2. Okay, so I'll just do one thing. I'll just write it again. This s square I'll write again. So it will be, if we solve it, 8 minus 42 divided by 2. It's minus 34 by 2, that is 17, minus 17. Similarly, 2 and 2 goes, this is 23. Okay, now how I will populate the other row? Similar way, in similar way, I'll just multiply this 17 with this 14, 23 with this 2, and multiply with 17. Okay, so when I multiply, when I manually calculate it, I'll get 16.705. Keep your calculator ready. This will be 0. Then the last term, see, I multiply this minus this is 0. Then again divided by 16.705, so it will be 23. So you have populated all the rows. Sorry, all the rows you have populated. Now what do you have to do after this? After this, you have to examine the number of sign changes in the first column. So after this, just examine this. Just examine this first column and see how many sign changes are there. Okay. So if we see from going S3 to S2, I am going from plus to minus. There is one sign change, and from S2 to S1, I am going from minus to plus. So there are two sign changes. There are two sign changes. One was from positive to negative. When you go from S3 to S2, it is positive to negative. And other one was from S2 to S1, it's negative to positive. There are two sign changes. And RH criteria says the number of sign changes gives me the number of poles in the RHP. Okay, so RH criteria says number of sign changes equal to number of poles in the RHP, or number of roots in the RHP. So it means for this problem, we have two poles in the RHP. It means, what was the question? How many roots of PS will lie in the RHP? So there are two poles. So there are two roots in the RHP. So that is given by Routh-Hurwitz criteria. We got it. Now, assume that this was the characteristic equation of a system, of a transfer function. Then the system would have been unstable. Why? Because there are two sign changes. It means there are two poles in the right half plane. So when any of the poles is in right half plane, the system is unstable. So basically, just remember, all the coefficients should be of the same sign for the stability. So we'll solve some other questions. Then and only there will be no sign change, right? So if all they are negative or all are positive, then your system is stable and no pole will lie in the right half plane. Okay, so for this question, you have two poles, they lie in the right half plane. Perfect. Now I will I assume that you already know this concept and you have done some questions. So we'll directly begin with now good questions, right? Now consider the following polynomial. P of s is equal to s5 plus 5s4 plus 11s cube plus 23s square plus 28s plus 12. Now the question is using RH criteria, comment on the system roots, on the imaginary axis. You can start solving by the time I give options. Option A is system has no roots on imaginary axis. Option B, system has multiple roots at the origin. Option C is roots on imaginary axis are plus minus 2j. Option D is roots on imaginary axis are plus minus 2j comma plus minus 2j, that is repeated roots on the imaginary axis. So these are the options. Okay, now let's see. By solving this question, we will get answers to many questions, and this will clear all your doubts, or you will be able to solve all RH criteria based questions just by solving this one question, because every other question that we solve will have the same concept, just there will be either a block diagram, you will have to solve the block diagram, or there will be some controller, or you will have to find relative stability, what values of k will do this, will do that. But basically the concept of all the RH criteria problems is the same, is the one which is in this question. So you are given a polynomial, right? It is a fifth order polynomial. So first of all, just tell me the number of roots. How many roots will be there in this poly? Like how many roots are there? Number of roots. How many roots are there total? Anyone? Yes, please. Shamita, you are raising your hand. You can ask your question if you have any. Or is it by mistake? I don't know. Shamita, you have a question or?
By mistake.
Okay.
By mistake, sir.
Yeah, no problem. I can just lower it. Yeah, okay, fine. So first of all, we have to see how many roots. So if the highest power of S is 5, it means there are 5 roots in total. Now in the question it is given, comment on the system roots on the imaginary axis. Okay, so we will formulate a Routh array. Then we will see if there are any sign changes, they will give me the roots on the right half plane. But how would I know the roots are on the imaginary axis? Are you getting me? So if I follow, as we saw in the earlier question, by using Routh criteria, if there are any sign changes, then we can say the roots are in the right half plane. Otherwise, all the roots are in the left half plane. If there are no sign changes, all the roots we assume they are in the left half plane. If there are any root on the right half plane, then there will be sign changes. But how would we find the presence of roots on the imaginary axis? That we will understand from this question. So let's first find the make the Routh array. Okay, so I'll make a Routh array. It's S5, it's S4, S3, S2, S1, and S0. What will be this? It will be 1. If anybody has any question, be it basic, just tell me, because we are just building our level, because we will be solving some tough questions. So if you have any questions in these simple questions, just let me know so that you will be able to understand other questions easily. Okay, so I just wrote this this RH. I just made this array. So and I populated this first and second row. Perfect. Now, what are the ways? I told you some of you joined late. So the ways to populate other rows is very simple. For this S3, we'll multiply these two, like it will be 5 into 11 minus 23 into 1 divided by 5. Okay. Similarly, the other will be 5 into 28 minus 12 into 1 divided by 5. Okay, but it will take a lot of time if I do these calculations. So it's better you have your calculator with you. Just quickly you find you populate these rows. So when I populate it, it will be S3 will be 6.4. This will be 25.6 and this will be 0. And S square will be 3. This will be 12. This will be 0. Now see, if you have calculator with you, just multiply 3 into 25.6, you will get 76.8, and 12 into 6.4, you will get 76.8. So this here, I will get a 0 element. Okay. Then you see 3. So when you got the 0, now see the other is already 0. 3 into 0 is 0. 6.4 into 0 is 0. So you got a 0 here as well. Obviously, there will be a 0 because there is no term left. So what you got here is the row of zeros, So remember, from now onwards, I'll just write it for you. Presence of row of zeros. First of all, there is one thing called any zero element. That is different thing. So if there was a 0 in the first row, that is different thing. But if you have the whole row as 0, if you have the whole row as 0, then presence of row of zeros indicates the occurrence of poles on imaginary axis. So if you have row of zeros, that means there are some poles on the imaginary axis. Irrespective whether the poles are repeated or not repeated, they are simple or repeated, you don't care. But yeah, for the time being, whenever you get a row of zeros, it means yes, the poles, there are some poles which are on the imaginary axis. Okay. So I skipped one type of questions where you get, for example, you get a 0 element here, not here, here. You will get a 0 element, but this will be non-zero. So you do one thing, you just replace that with epsilon, then keep keep the process on, keep the process going, and you'll get the answer. That epsilon is a very small positive number. Okay, so I told you in the beginning, this I have already explained in one of my previous lectures for the other semester. In that lecture, it's everything is given in detail. So here I will solve some good questions which will give you confidence, because if you solve those questions, you should be able to solve any question based on this RH criteria. Perfect. So as of now, whenever, just remember, whenever there is a row of zeros, that means there is a presence of zeros, there is a presence of poles on the imaginary axis. Perfect. Now, how to handle this row of zeros thing? See, this row is 0, this S1 is 0. So S1, I'll just make it here. S1 is 0 and 0. Perfect. S1 is 0. So what we do, this S square was 3 and 12. And this is S0. Now see, how we deal with this row of zeros is that we find the auxiliary equation, right? So we will find the auxiliary equation which is given by a row which is built by using the elements of row just preceding the row containing rows of zeros. Okay, so just preceding this row of zeros, we have s square. So we will use s square to find the auxiliary equation. So my auxiliary equation will be as, which is given by the elements of by using the row which is just preceding the row of zeros. So I'll use 3 and it is s square plus 12 equal to 0. So I made this auxiliary equation. How I made it? Just by making use of the elements of the row just preceding the row of zeros. Then after this, we differentiate it. I differentiated dAs by ds, and what I will get 6s. Okay, 6s plus 0. Okay, so I got 6s plus 0. Then I will use the coefficients of this derivative of auxiliary equation to populate my row of zeros. So in this case, my coefficients are 6 and 0. So now I will populate my row of zeros as this. See, S1 will be 6 and 0. So I got rid of this row of zeros. How? I made an auxiliary equation. I made the auxiliary equation which is built by using the elements of the row just preceding the row of zeros, and then I differentiated that auxiliary equation. The coefficients of the differentiated auxiliary equation gives me the coefficients for the row of zeros, new row for the row of zeros. So I built new equation for this row of zeros. Okay. Then after this, the last one is calculated again using the same concept. This into this minus this into this divided by this term. So what will be my last? It will be 6 into 12 divided by 6. That will be 12. So I'm done. I'm done from making the by from populating the RH array. Okay. So now see, is there any sign change? Is there any sign change? So there is no sign change. So it means there is no root on the right half plane. So I'll write here no sign change, no sign change equal to no root in LHP. But the question is not related to that. That we know. Oh, sorry, not LHP, RHP. The question is about the occurrence of poles on the imaginary axis. See, so but there is no sign change. There will be no poles on the RHP, but there is a row of zeros. It means there are poles which are there on the imaginary axis. And the question is find those poles, because the question is actually about them. So we have to find those poles and see whether they are simple, multiple, etc., etc. Now, how do we find the poles on the imaginary axis? If we have to find, so there is row of zeros, we made auxiliary equation. We will, to find the poles, we will go to auxiliary equation, which is 3s square plus 12. Put it equal to 0. Okay, and we will solve this auxiliary equation. The roots of this auxiliary equation are the poles on the imaginary axis. Okay, so it's the roots of this auxiliary equation. So what are the roots of this auxiliary equation? It will be 3x square equal to minus 12. 3, this is 4. So s square is minus 4. My s will be plus minus 2j. Okay, so my poles, they do lie on the imaginary axis. Two poles are lying on the imaginary axis, and their location is they are plus minus 2j. Okay, so plus minus 2j is the location. Now tell me, based on this, tell me what is the answer. Which option is correct? Anyone? Which option is correct? Suraj or Shubham, Tarun Raj? Tell me which option is correct.
Third option, sir. Third option.
Okay, very good. So third option is correct. So our poles, they do lie on the imaginary axis and the number is plus minus 2j. Very good. Now see, look here, one more thing. There is no pole on the right half plane, but there are poles on the imaginary axis, which eventually are given by this auxiliary equation. So I told you, I will tell you, or people will tell you when you solve questions on RH criteria that if the number of sign changes, the number of sign changes will give you the number of poles in the LHP. So whenever there is a sign change, then and only my system can be unstable. Okay, but that is not the case. Even if there is no sign change, still your system can be unstable. That will be determined by the poles at imaginary axis. So if my poles at imaginary axis are repeated, then in that case your system can be unstable. Okay, now let's solve another question. Rows of zeros is a very important concept, and the key takeaway from this question is that presence of row of zeros gives the poles on imaginary axis. Now another question. Consider now see, from now onwards, I'll mix up two things. Either I'll use feedback or I will use controller with this RH thing. Okay. So because we have learned feedback, consider a unity feedback. So when I write this unity feedback, something should come in your mind. Even if I do not make the block diagram, still something should come into your mind when I'm writing the unity feedback. Consider a unity feedback system with forward path transfer function g of s, which is given by k into s plus 3 into s plus 5 divided by s minus 2 into s minus 4. So this is my forward path transfer function. Okay, there's a k and some poles and zeros. The range of k, the question is the range of k. These type of questions you also get in GATE. The range of k to ensure stability is. Everybody try to solve it. My option number A is k greater than 6 over 8. My option number B is k less than minus 1 or k greater than 3 over 4. My option number C is k less than minus 1. My option number D is minus 1 less than k is less than 3 by 4. Yeah, please solve it. Or anyone can give me an idea, then we can solve it.
First,
Can
we need
somebody?
to
Yes, please.
find out the closed loop transfer function, sir.
Very good. I'll write closed loop transfer function. Then
The characteristics equation we always take in denominator form, sir.
very good. Characteristic equation. Then we will go with characteristic equation. Then
we need to apply route array.
okay, very good. Route array, RH criteria. Then we will get some condition. Perfect. So
Yes, sir.
yes, thank you, Dhanraj. So this is actually the process that we'll follow. See, you have to understand questions are very easy whenever you're solving a control problem. If you have not understood control, it will look very difficult. But if you have understood it, you will do question. You can just visualize it. Howsoever difficult it is, it doesn't look difficult then. Okay. Now see how we will solve it. We are given an open loop transfer function, right? So we are given g of s. We are given g of s. But for stability, we always check the roots of characteristic equation, which comes from the closed loop transfer function. So basically, we will find the CLTF. We will find CLTF. So also it is given unity feedback. It means my h of s is 1, my h of s is 1. So what will be my transfer function? My transfer function will be g of s divided by 1 plus g of s, because h of s is 1. Okay. Now this 1 plus g of s, which is the denominator of my closed loop transfer function, uh, and this is the characteristic equation. This is the characteristic equation. Okay. So I'll just put in the value of gs. When you put in the value of gs, you will get something like this: k into s plus 3 into s plus 5 divided by k plus 1 s square plus 8k minus 6 into s plus 15 15k plus 8. This is the constant term. So for you, I'll just write it like this. So my characteristic equation is k plus 1 s square plus 8k minus 6 into s plus 15k plus 8. Now see one thing. This is just a second order system. So no need to make a route criteria. Why? See, I told you, when from a Routh-Hurwitz criteria, we can say the system is stable because we have to check stability here. There should be no sign change. Okay. Because if there is any sign change, that means my pole is in the right half plane. So there should be no sign change. So either all these coefficients should be positive or all these coefficients should be negative. Okay. So if I take case number 1, which means all coefficients are positive. So if all coefficients are positive, it means k plus 1 should be greater than 0. Okay, it implies my k is greater than minus 1. Similarly, 8k minus 6 should be greater than 0. It implies my k is 6 by 8. My k is, let me see, what is 6 by 8? 6. That's 3 by 4. So my k is greater than 3 by 4. And then another thing is 15k plus 8 should be greater than 0. It implies my k is greater than minus 8 over 15. This is 0.75 and this is 0.5 minus 0.53. Okay, now see, we can see the range from here. So let's assume this is k, or not like this. This is number line. This is 0. This is positive. This is negative. So my first is k should be greater than -1. So if this is -1, then my first condition says my k should be greater than this. So this range should come and this range should not come. Okay, my k should be greater than -1. Then my second option is saying my k should be greater than 0.75. So let's assume my 0 is here, so 0.75 will be here, and 0.5, okay, there is one more point which is here, minus 0.53. So another question is, another says my k should be greater than this. It means the intersection is what? Intersection is this part. So from this case, we can say my k should be greater than 0.75 or greater than, not like this. So which is 3/4. So from this condition we get, when all the coefficients are positive, my k should be greater than 0.75. Now take another case 2. Because I told you from RH, the coefficients should have the same sign. All coefficients are negative. All coefficients are negative. Then and only the sign will be same. So what does this mean? This means my k plus 1 is less than 0. It implies my k is less than -1. Similarly, my 8k minus 6 is less than 0. It implies my k is less than 0.75. My third is 15k plus 8 is less than 0. It implies my k is less than -8/15, which is equal to -0.53. Now see, same scenario. If you see here, then you will get this part. You will see this part because -1, it should be less than -1. This part is coming. Similarly, if it is less than -53, this part is coming, and -75, this part is coming. But you have to take the intersection only. You have to take the intersection only. Okay, the intersection is, so from here you can conclude your k should be less than -1. Now, based on this, tell me which option is correct. Now tell me which option is correct based on this. Did you understand, or I need to explain it again? Option B is correct. Why? Because k is less than -1. Either this is condition or k is greater than 3.4, which is actually 0.75. You can see it from here. Okay. Okay, no problem. You will get to understand in other questions. Let's solve another good question. Let's see. I will make it easy for you. This question, I'll make it easy for you. The closed loop transfer function is given as d of s is equal to s cube plus 3s square. Everybody should be able to tell me the answer in this case, because this is a good question at the same time, a very conceptual one. S5 minus 2s4 plus 3s cube minus 6s square plus 2s minus 4. This is my closed loop transfer function. The number of poles in the LHP, in the RHP, and on the j omega axis are. The question is, find the number of poles in LHP RHP and on imaginary axis. See, total poles will be 5 because characteristic equation is fifth order. I'll give you options. 212, B 014, C 104, D 122. See, total poles are 5. You have to find how many are there in the LHP. Okay. You can see one thing you can decide from options. See, imagine this one is imaginary, 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 imaginary. So it means definitely there are imaginary poles. Okay, so definitely there are imaginary poles. It's given because all the imaginary options are present. It means when there are imaginary poles, it means there is a presence of row of zeros in the RH array. So when there is a presence of row of zeros in the RH array, then you will find the auxiliary equation and solve the auxiliary equation. That auxiliary equation should give you the poles on the imaginary axis. The question is simple, but I will ask you again the locations of those poles on the imaginary axis. First tell me the answer of this question. It's very easy. Just make RH array. Then see, is there any sign change? The number of sign changes will give you the number of poles in the RHP. Otherwise, all poles are in the LHP. And if there is a row of 0, then make auxiliary equation, solve that auxiliary equation. The number of poles on the imaginary axis will be given by the order of the auxiliary equation. Any doubt to anyone? Please tell me. I'll just make this array S5, S4, S3, S2, S1. 1, 3, 2, -2, -6, -4. Yes, please. Anyone? Somebody wrote the answer, Suraj. Suraj is saying 4 poles. What? 4 poles are where? 4 poles are where, Suraj? Which option do you think is correct? Four poles are in the on the RHP. Oh, is it? I don't know. I'll just check. We'll solve it. Anybody else? Anybody else coming up with the answer? Which option is correct according to you, Suraj? Which option according to you is correct? Shamita, can you tell me 014? Okay, Suraj is saying 014. So option B. Anybody else with this option? Which one, Shamita?
Option B.
Very good. Yes, option B is the correct answer. Now, can any one of you tell me the pole location on the imaginary axis? Or at least tell me the auxiliary equation. What is the row of zeros? Anybody, what is the row of zeros? Which row is the row of zeros? Tarun Raj, which row is the row of zeros? Which row?
S3 is row of zeros, sir. S4
Okay, this row. This row is the row of zeros?
Yes, sir.
Then what we will do, we will make auxiliary equation. So what will be the auxiliary equation? Is this correct? Whatever I wrote, is this correct? Sir. Auxiliary equation, Shubham?
Yes, sir.
Okay. Now can anybody solve this and tell me, because the roots of this equation are the roots on Suraj plus minus J1 plus minus. Very good. Very good. So, Suraj, what is wrong with your mic? Why don't you unmute and speak? So, Suraj is saying the answer is plus minus root 2j and plus minus j. So, there are four roots on the imaginary axis which are given by this. Now, Shamitha, can you tell me whether the system is stable or unstable? Shamitha, can you tell me whether this system is stable or unstable?
Stable, sir.
Stable? How? How many poles are in the RHP?
I'm unable to see the screen, sir.
Oh, is this with any other? Is the problem with this with uh, any other person in the meeting? Then I can just check on. Is my screen visible to others? Is my screen visible to others? Darun Raj, is my screen visible to you?
Yes, sir. Visible, sir.
Okay. 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 Shamitha, you can just like leave the meeting and then join again. Then maybe it will be clear to you. It will be visible to the screen. So let me explain. Let me explain. See, this is the complete RH array that you will get. You'll see there is one sign change from positive to negative from S5 to S4. So it means at least there is other, and after this all are negative. So there is no sign change afterwards. So it means there is one pole in the RHP. So even if there is one pole in the RHP, that will make the system unstable. This system is unstable. But if there would have been no poles in the RHP, then the system would have been what? So I'm asking this question to Darun Raj. So let's assume there is four poles are on the imaginary axis as we saw, and one pole which is in the RHP that is in the LHP. Then tell me what will the system be? It will be stable or marginally stable or unstable?
Marginally stable.
Very good. So
Unstable.
it will be no, 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 no. Tell me, yes, tell me first. Is it you stick to your answer? Think and tell me. Will be stable, unstable, or marginally stable? Anybody else can also unmute and ask. Will be stable, unstable, or marginally stable? Assuming there is no pole on the RHP, this pole is on the LHP. We will
Okay, sir.
make
Now marginally stable, sir.
the graph. See, this is sigma j omega. As of now, we got one pole in the RHP and other pole. One is at plus minus 2j and other is at, so these are the locations, plus minus j and plus minus root. I'll just write it. This is root 2j, this is j, this is minus j, this is minus root 2j. Okay. So this was my earlier pole location, but in this case, my pole is in the RHP. This makes my system unstable. But I'm saying this pole is in the LHP. Now tell me whether my system is stable or unstable or marginally stable. Now, Darun Raj, can you tell me?
And now
Is it
marginally stable.
unstable, sir?
Jaya Sudha, how is it unstable? Can you please explain? This pole is not there. This pole I have shifted to LHP. I told you in the beginning that if the poles on the imaginary axis, yes, 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 please, please.
Multiple poles on the imaginary axis makes unstable, sir.
No, 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 no. The multiple poles, but the condition is they should be repeated. Here they are not repeated. So this system, if this pole is shifted to LHP, is a marginally stable system. Okay, because this is how the examiner will trick you in the exams. So the only condition when your system poles, if present on the imaginary axis, contribute towards the instability, is that they have to be repeated. Be it anywhere, they can be on zero, on the anywhere on the imaginary axis. If they are repeated, then your system is unstable. So now let's see another very interesting question. But yeah, this question is easy. That's why I hope everybody should be able to answer this. But again, I'm mixing up two concepts here. So consider this block diagram, plus minus. So when I make this plus minus, quickly you should be able to think, oh, this is a unity feedback system. Okay, so you are given this system where my G of C is equal to K over S, and G of P is equal to 1 divided by S plus 1 into S plus 5. Okay, this is the question. You are given forward path transfer functions and a controller transfer function, which is K by S. You have to find, the question is, find the range of K for which the closed loop system is stable. So basically in control, first task is to understand the question, because if you have understood the problem, it's 80% solved. Your options, try to solve. Your options are 0 is less than K is less than 30. Option B, minus infinity is less than K is less than 0. Option C, 0 is less than K is less than infinity. Option D, 5 is less than K is less than 30. I'll just explain. So this is your R of T. I'll give you hints. So first of all, you are given a unity feedback system. So you are given these two control systems. They can be anything. So this is actually the plant, and this is some controller which is using some gain K, trying to make system whatever is the objective. So first of all, they are in cascade, so their transfer functions will be multiplied, and then after that you will find the closed loop transfer function. So you will then, from the closed loop transfer function, you will find the characteristic equation. Okay, so it's very easy. So from the characteristic equation, then things will be easy to visualize. So can anybody tell me what is the closed loop transfer function that you got? Please, everybody solve it. It's not that difficult. You just have to do, okay, I'll write it here. Your transfer function, closed loop transfer function, will be G of C into G of P divided by 1 plus G of C into G of P. This is it. And this is my characteristic equation. Can anybody tell me what is the, okay, I assume you find the transfer function. Shamita, have you found it? If you have found it, please tell me your characteristic equation. Or can anybody tell me what is the characteristic equation?
K plus S into S plus 1 into S plus 5.
No, okay. Okay, I'll write it. You just solve your characteristic equation and tell me, is it like this?
Yes, sir.
Yes, sir.
Perfect. Now what is the way? What is the other way? We have to find the stability range of K. So let's make the route array, S cube, S square, S1, S0. It will be 1, 5. This will be 6 and K. Now, what will be this S1? S1 quickly, 30 minus K divided by 6. This will be, then the other element will be 0, and this will be K. Is it clear to everyone how I wrote this array? Anybody has any doubt in this, how I wrote this array? Because we have been
No, sir.
seeing it from the last couple of questions. Okay, now tell me, now we have to find whether the system is stable or not. It means all the coefficients should be of the same sign. So we know this is positive, then this should be positive, this K should also be positive. Okay, because then and only there will be no sign change, then and only there will be no pole in the RHP. Now see, when it means all of these coefficients should be positive. It means your K should be greater than 0, first of all, from this condition, and your 30 minus K divided by 6 should also be greater than 0, which implies 30 minus K is greater than 0, which implies my K is less than 30. Okay, so I got two conditions. One is my K is greater than 30. Other condition is my K is less than 30. Now from the options, tell me which option is correct. Darun Raj, tell me which option is correct based on the answers we got.
First option, sir.
Option A,
Very
sir.
good. Yeah, option A. Option A is the correct option. So anybody has any doubt in this question? Very simple question. And you get these type of questions in your exam, in your final NPTEL exam, in your GATE exam, and all other semester exams. Now let me make this question complicated. Okay, we'll just build on. From this question, we'll just build on. Now the question is, the value of K, you have to keep this question into mind, this system into mind, and this characteristic equation into mind. Now from this, the question is, the value of K for which the system is marginally stable. Now here your concept will be checked. Now the value of K for which the system is marginally stable is, please solve it. Everything is given. So you have Routh array is there, you have characteristic equation given. So you are being asked, okay, for what value of K the system will be marginally stable. Now if you can see here, I told you there will be marginally stable means the poles are on the imaginary axis. And I told you when there is a row of zeros, then that means the presence of poles on the imaginary axis. So when the poles are on
K is equal
imaginary
to
axis,
30.
K equal to 30. Very good. So K equal to, why K equal to 30? See, by putting K equal to 30, if we put here K equal to 30, then my S1 will be 0 and 0. So I will get row of zeros. So when I get row of zeros, it means my system is marginally stable. Why? Because still we can say at least my system is marginally stable. Why? Because the poles are on the imaginary axis. But there is one thing. Presence of poles on the imaginary axis do not guarantee always the system is marginally stable. Okay? The system can be unstable as well. So now, can you check here? So Darun Raj told the value of K should be 30 so that the system is marginally stable. Perfect, correct. Why? Because by making K equal to 30, we'll get poles on the imaginary axis. But my question is, at this value of K, where my system is marginally stable, can you find the pole locations? Because this question is partially correct. I told you because the presence of this only gives me the presence of poles on the imaginary axis, but it does not give me the pole locations. So in order for you to say the system is marginally stable for k equal to 30, you have to check the pole locations as well. And how do you check the pole locations? You got the row of zeros when you put k equal to 30. When you got the row of zeros, then you find the auxiliary equation, which is found from the elements by using the elements of the row preceding the row of zeros, which is s square in this case. So my auxiliary equation will be 6s square plus k equal to 0. Okay, so this is my auxiliary equation, but we already know the value of k for the system to be marginally stable is 30. So it means my 6s square plus 30 is equal to 0. It means my s square is minus 5. It means my s is plus minus 5j. It means my poles on the imaginary axis, they are plus minus 5j. They are not repeated. Therefore, my system is actually marginally stable at my k equal to 30. Is it clear? Is it clear?
Yes, sir.
Anybody has any doubt here? Jaya Sudha, any doubt? Okay. Now let me make it more complex. I'll ask you a question this way. At the value of k, where the system is marginally stable, no, not this. Wait. No, not this question, because this we did. Well, I'll ask you that in the other question. Okay, so you got the pole locations from this question. So I hope this question is clear. So what did we see in this question? Initially, we were given a control system. Then we were asked find the value of k for which the system is stable. So we were given a unity feedback system. So from this unity feedback system, what did we do? We just solved it, got the characteristic equation, which is given by the denominator of the closed loop transfer function. So, and then from the characteristic equation, we formed a Routh array. From the Routh array, we checked, okay, the coefficient should have the same sign. And from that, we reached at a condition of k for which the system is stable. Then I asked you to find the value of k for which the system is marginally stable. Then we know the system will only be marginally stable if the poles will be on the imaginary axis. So we put that, we and there should be a presence of row of zeros. Okay, so we did that, and then what did we find? We find the value of k equal to 30 will do that, will give me a row of zeros. And yes, that was actually correct, because when we found the pole locations, they were actually not repeated. That means the system is actually marginally stable. Now, based on this, we will do some more questions. Okay. Now see another very good question. We have learned PID controllers. So basically, I have a PI controller here coupled with a control system. So there will be all the concepts together now. So that's how you get questions in gate. So you have some reference signal, plus, minus. You have a PI controller. So when it is a PI controller, your transfer function will be like this. Then you have GS, which is 1 divided by S plus 1 into S plus 2. This is your Y. Then you're feeding this back like this. So basically you have a PI controller with a transfer function. The question is find the range of controller gains K and Ki such that the feedback system is stable, So you'll get questions like this in exam. There will be nothing like find, given a polynomial, find whether the system is stable or not. There will be questions which are mixed. Okay, such that the feedback system is stable. Okay, anybody can explain me how? Because we solved. Achha, okay, I'll give you options. Because that will help you to give me answers. Option number 1 is Ki is greater than 0. K is greater than 0. Option number B, K is greater than 0. Ki is greater than 3Ki minus 2. Option number C is K is greater than 1 by 3Ki, comma, Ki is greater than 0. And option number D is K is greater than minus 5, Ki is greater than 2. Okay, so you're given an open loop transfer function here and a controller here. Then you're being asked the question about the feedback system. So you eventually have to find the closed loop transfer function. So what will be your closed loop transfer function? I don't care. I only care about characteristic equation. So your H of S is 1. Again, following the same pattern from the previous question. You just have to multiply the two. So I'll just write it for you. GS will be SK plus KI divided by S cube plus 3S square plus 2S. So this is my GS. I've given you GS. I have given you HS. Now, can anybody tell me what is the characteristic equation? Because that is important to us. The denominator, basically. So this is my characteristic equation. Anybody? Did all of you get the same equation? S cube plus 3S square plus S into 2 plus K plus Ki equal to 0. Now again, let's solve it. Let's make RH array, Routh array. Let's make RH array. So I'll write S cube, S square, S1, and S0. My first element, of course, 1 and 2 plus K. My second element is 3 and Ki. Then it will be 6 plus 3K, 6 plus 3K minus Ki divided by 3. This will be 0, and here it will be Ki. Now, every one of you should tell me the answer. So for the system to be stable, all the elements should be positive because first and second element is positive. It means my Ki should be greater than 0, and my 6 plus 3K minus Ki divided by 3 should be greater than 0. It implies my 6 plus 3K should be greater than Ki. It means, what does it mean? It means my K should be greater than Ki by 3 minus 2. Okay, here it should be minus 2. So option C is correct. Everybody got this? How I wrote this? Very simple. All the coefficients should be of same sign. So your first two coefficients are positive. It means your third and fourth should also be positive. Then I just wrote them to be positive, solved it, and got the answer. Now let's make this question a bit complicated. The same way we did it for others. Now in this question, find the value of ki and k such that, very interesting question, the closed loop poles such that the closed loop poles are at s equal to -1 and s equal to -1 plus minus j. Please solve it. So you are given the pole locations. You know the characteristic equation. You see, characteristic equation is third order. That's why there are three poles. So you are given characteristic equation and you are also given the poles and you are being asked to find the values of ki and k. See how I will solve it. Can you form the characteristic equation based on the poles? Of course you can, because you are given all the three poles. So can I write it like this? This s minus 1, this s equal to -1 and s equal to -1 plus minus j. Can I write it like this? S plus 1 into s plus 1 plus j into s plus 1 minus j equal to 0. That's what, because they are the poles. Okay, so then I can solve it like this. A plus b into a minus b. It will be a square minus b square. Fine, so I can write s plus 1. Now this I will solve. A square minus b square. So it will be s square plus 2s plus 2. And finally, when you solve it, you'll find s cube plus 3s square plus 4s plus 2. This is the equation, characteristic equation actually, because the poles are of the characteristic equation because it's closed loop. But already you know the characteristic equation, that is s cube. The characteristic equation which is given, which we found from the control system by using feedback, is 3s square plus 2 plus k into s plus ki. Okay, so now let's compare these two equations. It means my 2 plus k should be equal to 4 and my ki should be equal to 2. So it means my k should be equal to 2 and my ki should be equal to 2. Understood? Anybody has any question here until here? I can explain. Please ask. Okay, if you do not have any question, then solve this question. Now we have found the value of k and ki to be equal to 2. Consider the value of k found above. That means consider k equal to 2. Then the closed loop system, this is very important problem. You will get these type of questions in your gate. Then the closed loop system oscillates at a frequency dash. Then you have to find so if we are given the value of k is 2, which is said, it's given, consider the value of k found above, then the closed loop system oscillates at a frequency of what? It means, see, whenever you are given this thing oscillates at a frequency of, it means obviously there are poles on the imaginary axis, then and only system will oscillate. Otherwise, either the system will be unstable or the system will decay down. See, I'll show you here. If my poles are on the RHP, so if my poles are on the RHP, then your system can be like this, or your system can be like this, anything, but it will go to infinity. If your poles are on the LHP, then your system will be like this. Okay? Or it can be like this as well. Okay? Anything, but it will decay to zero. If your poles are on the imaginary axis, and they are not repeated. If they are repeated, they're like this. But if they are not repeated, then they are marginally stable. They will oscillate. They will oscillate. They will not be stable. They will not be unstable. They will be marginally stable. It means they will oscillate with a frequency. That frequency you have to find here. So what will be the frequency of oscillation if the value of K is 2 in the above problem? Or in other words, that means what does that mean? That means there is, of course, the system is marginally stable. It means there are poles on the imaginary axis. It means there is the presence of a row of zeros. Okay, now see, go to the this array. When my K is 2, put this K2 here. 6 plus 6 minus Ki. Ki is what? So it means Ki should be 12. You have to find the system. So this will be 0. Why? Because it's given the system oscillates at a frequency. So I'll write it here. 6 plus 3K minus Ki divided by 3. Now this should be 0. Why? Because it's given, it oscillates at a frequency. It means there should be a row of zeros. But we know my K is given as 2. So it's my 6 plus 6 minus Ki by 3 equal to 0. So it will vanish up. My Ki will be equal to 12. So I got my value of Ki to be 12. Now when this will be row of zeros, I will find the auxiliary equation. So my auxiliary equation will be 3s square plus Ki equal to 0. Ki is 12. 3s square plus 12 equal to 0. S square is equal to minus 12 by 3. S square equal to minus 4. Or
The
S
Ki
is
is 4.
equal plus minus. Sorry, what?
Ki is 4 no, sir.
No. See.
Find
Okay.
the equation.
Ki is 4. Of course, we have found. No, Ki is 2. But the question is not saying that. Question is saying consider the value of K, not Ki. So we have to consider the value of K. That is, we have to find K to consider K equal to 2. And it is given the system oscillates at a frequency. So when system is oscillating at a frequency, it means there are poles present on the imaginary axis. Try to understand. When there are poles present in the imaginary axis, then I told you in the beginning, there is the presence of a row of zeros. It means this will be 0. This row will be row of zeros. And when you put K equal to 2, you will get something like this. 6 plus 6 minus Ki 3 equal to 0. There you find the value of Ki. It's a new value of Ki for which there will be oscillations. Understood?
Yes, sir.
Okay, so now see what I did. Then I found the auxiliary equation. I solved the auxiliary equation. I found the roots. Now the system is again marginally stable. The system is not unstable because the roots are not repeated. Roots are distinct, but they are on the imaginary axis. It means the roots are there, the plus minus 2j. So it will be marginally stable. But what is the frequency? Actually, if you see, this is j omega, right? I always write this S is sigma plus j omega. This omega is the frequency of oscillation. Okay. So here the frequency of oscillation is, then what is the frequency of oscillation here? The frequency of oscillation is 2 radians per second. Okay. So the frequency of oscillation is 2 radians per second. I hope this is also clear. Oh, what's the time left? Oh, we have time. We can solve 2 more questions. Anybody has any doubt? We're going to solve one very, very interesting again that will use all the concepts. If you have any doubt until here, we can discuss. Consider an OLTF. Yes, yes, please.
Sir, if poles are repeated, then there is oscillation will present. Okay.
No. If poles are on the imaginary axis and they are repeated, then the system is unstable. So then your response will be like this. That will go to infinity. Give you any. We discussed it in the second week when we discussed bounded input, bounded output stability. So you will give any bounded input, your system output will be unbounded. It will go to infinity. There is, it is unstable because we discussed. See, the system is stable if the poles are on the LHP. We discussed it in the beginning. You joined late, probably. Yeah, here, see. If the poles are on the LHP, the system is stable. If the poles are on the RHP, the system is unstable. If the poles are on the imaginary axis, but they are not repeated, then the system is marginally stable. If the poles are on the imaginary axis, but they are repeated, then the system is unstable. But as of now, we only saw the cases where my system poles were on the imaginary axis, but they were not repeated. So the system was marginally stable. If they would have been repeated, then the system poles, then the system would have been unstable. Now see, this question, I want everybody to answer this question. So this is a very good question. I'll give you options as well. So you're given an OLTF, an open loop transfer function. Then what is the value? This will cover the concepts of earlier weeks as well. What is the value of H? So my H is feedback. That will result in the roots of the characteristic equation at -1/2 plus minus j root 3/2. Option A, H is 3. Option B, H is -3. Option C, H is root 3/2. And option D, no such value of H exists. See, I'm giving you, you have an open loop function and you are given a feedback H, and it's not mentioned. It's a unity feedback. It's not unity feedback, of course, but it's not mentioned it is negative or positive. Whenever I told you, I've told you this before as well. Whenever there is nothing mentioned about the feedback, of course you should take negative feedback. We have discussed why. We have solved questions as well. So take negative feedback and find the characteristic equation, right? And by taking H as H, by taking feedback as H. Okay? Solve it, please. Yes, please solve it. I'm doing something else. I'm not solving the question. Don't see me. I gave you some idea. I wrote something here. See, you are given an OLTF. You are given an OLTF. You are given a feedback, H, and you are given it's a negative feedback. And you're also given poles. From poles, I can find the characteristic equation, and from the closed loop system, I can also find the characteristic equation. Suraj has written 2s minus 1. But tell me the option. Tell me the option. So you will get characteristic equation from the closed loop system. You will get characteristic equation from the poles. Then you compare. Is there any value of h that is given or not? So in this question, the answer is this is your the Suraj has solved it. Suraj has actually solved it, and basically you just have to do don't have to do anything. Just write this equation, solve it, you'll get some equation, and also find the characteristic equation from the closed loop transfer function. We have did this question, then just compare. Then you'll find there will be no such values of h, which are given in the options. Okay. One last question. One last question. And here maybe we'll get the answers. In the above problem, oh, I'll write it homework. Please solve this question. If you are sincere, then I hope that you will solve it. Now, in the above question, suppose h of s is equal to k into s. What is the value of k such that the closed loop pole, then what is the value of k such that the closed loop poles are at minus 1 by 2 plus minus j under root 7 by 2. Here you will get some answer. Suraj should be able to tell me answer quickly because you have already solved it. Yes, please, others as well. Please check and please try. Very simple. See, now your h changes. So in place of h, you will put k into s. So you'll put k into s, and then after that, you'll just compare. Okay, I'll do one thing for you. I'll just make this. I'll just evaluate, give you characteristic equation based on the poles. You just have to find the characteristic equation from two ways. Then just compare and you'll get the answer. You solve it, you'll get s square plus k minus 3 into s plus 2. This is your characteristic. This should be your characteristic equation. Oh, sorry. Characteristic equation should be s square plus s plus 2 equal to 0. Somebody has solved it. K equal to minus 2. You have solved it correctly, but you're doing a simple mistake. It will not be minus 2, it will be 4. So maybe you are doing minus 3 plus 1, but it's actually 1 plus 3. Just check it. Your K will be 4, Suraj. So what you will get from the closed loop system, your characteristic equation will be s square K minus 3 into s plus 2 equal to 0 on comparing C. K minus 3 should be equal to 1. It implies my K should be equal to 4. Is it clear, Suraj? Is this the equation that you got from the transfer function, or I can solve it for you? I'll just give you a hint. I don't know whether has everybody understood? Shamita, have you understood? What's the concept behind it? Or I can understand. I can explain because we have got some time. Or let's keep the session open to question answers, because that's all. That's it. We are not solving any further questions. I hope with these questions, you should be able to have understood the concept well. I made sure that you not only practice questions on RH, but also get a feel of what you have understood or what you have learned in the previous weeks, like controllers, like closed loop stability, closed loop systems, and other things as well. So with this, I hope you should now be able to solve all of the assignment questions. I've not checked the assignment problems, what they are exactly, but yeah, I would assume that they are not difficult than the questions we have solved. And if you have any doubt, you can ask now, based on whatever we have covered, or is whether there is anything in the assignment that's difficult, or anything else related to RH criteria. Shamitha, have you understood everything?
Exactly.
Do you have any doubt, or okay? Jaya Sudha, is all clear? Probably you joined late, but not sure.
I have a doubt related to gate exams.
Sorry, I'm not able to understand what I say.
I have a doubt on to gate exams.
Yes, please ask.
So how to prepare for a gate exam?
Just attend these sessions regularly for control. So in particular, I can only tell you about control. So just attend these sessions regularly, and you'll get to know things. Uh, uh, like your concepts will be they will build up accordingly. And one more thing that I would recommend is to solve after going through sessions, or after learning your concepts, and after going through this session in particular, this Sunday session, go and open previous year questions on the same topic, uh, previous year questions of GATE, and see if you're able to solve them. If you're able to solve them, done, you have understood. If not, learn again, go again, right? And proper make notes, properly, make your notes properly. That's very important. You're in third year or what?
Okay, sir.
In which year are you, Shamitha?
Third year.
Good.
Sir.
Keep attending. Eventually, at this point of time, it might look difficult for you, but yeah, I can assure you that by the time we keep on going, other weeks 6, 7, 8, and 9, uh, uh, you will get something. But just keep on watching and keep on learning and keep on practicing more and more questions. Anybody else? Any doubt? Jaya Sudha?
Sir, you have presented three graphs depending upon the pole location, that is on RHS and LHS and on imaginary axis.
Yes,
Will
yes,
you,
this one.
yes, sir. Will you explain the graphical representation, sir?
Perfect, perfect. Yeah. Okay. I'll explain it again for you. Then I'll come to Shubham. Shubham is preparing for gate. I'll come to you after this, Shubham. First, let me explain these things in detail. Just give me a moment. Excuse me. See, there are three things. First of all, we discussed it in the beginning as well. How do we check whether a system is stable or not? How do we check stability? Okay, how do we check stability? We check the poles of characteristic equation. I assume that you know how to find characteristic equation. I know how to find the poles of the characteristic equation. Now see, I'll make the graphs. This is my sigma, this is my j omega, because every pole, my s is a complex number which has a real part and an imaginary part. Now I'll plot. If you have a pole in the left half plane, let's assume only one pole. You have a pole at the RHP, so this is LHP, this is RHP, and we have imaginary axis. So if you have any pole in the left half plane, then your system is stable, and your graphical representation when your pole is real. So this is a real pole. See, there is no imaginary part. So in this case, you will have a decayed response, and your value will decay to 0 or settle to some number. Okay, it will have a exponential decay, right? So and the system is stable. Now let's consider this thing. The same graph, sigma, j omega, but you have a pole in the RHP. Okay, this time you will have something like this. It will go to infinity because the system is unstable. Why? The pole is in the RHP. This is easily visualizable if you see Laplace. Okay, because the response, if you have this can be thought of a system like 1 divided by s minus a. If you take the Laplace transform of this, you will get e raised to the power 80. So this will be unbounded. Similarly, this can be thought of 1 divided by s plus a. If you take the Laplace, it will be e raised to the power minus 80. Fine. Okay, now see one more criteria. Now I'll come to complex poles. So whenever I talk of complex poles, that means the system is at least second order because complex poles occur in pairs, sigma, j omega. Now see, let's assume you have complex poles. So complex poles always occur in pairs. So you have two complex poles, but they are in the left half plane. The response will be something like this. See. Okay, let me make it like this. So response will decay to 0. Why? Because it is a stable system, but it will have some oscillations because of this complex terms. Okay, there will be the presence of sinusoidal terms if you see the Laplace transform of this thing. Again, if you have a system where you have complex poles but on the RHP, then you will have something like this. This way, this time the system is unstable, right? The system is unstable, so you will have something like this. So the system will keep on the oscillations will keep on growing. Okay, so it will go to infinity eventually. Why? Because the presence of sinusoidal terms. Now one important thing is when you have, now this is your doubt, I know. Your doubt is, now this is sigma, this is j omega. Now, if your poles are of this location, they are on the imaginary axis, but they are complex. You know the response? The response will be like this. It will be marginally stable. Okay, now see. Again, I'll make the system has poles on the imaginary axis, sigma, j omega, but this time the poles are repeated. The poles are like this. Okay, the poles are repeated. The system will oscillate the same way I did it for unstable systems. Okay, it will keep on increasing and go to infinity. Why? Because no doubt the system poles are on imaginary axis, but because of the repeated poles, you see it's basically is related to this Laplace transform. Okay, now if you have one last two uh, cases, j omega, if you have a pole on the origin, if you have a pole on the origin, then your response will be something like this. Constant DC gain, sort of. The system is stable. Sorry, the system is marginally stable. Okay, because the pole is at the imaginary axis. And one last case, if your pole location is on the imaginary axis, but they are is on the origin, but repeated poles on the origin, then your response will be something like this. It will go to infinity. It's unstable. I told you. The roots, repeated roots on the like the repeated roots on the imaginary axis leads to instability. Is this clear, Jaya Sudha?
Yes, sir. Cleared, sir. Thank you.
Yeah, thank you. So basically, you just have to remember that whenever you have repeated poles on the imaginary axis, then your system is unstable. Now coming to Shubham. Shubham, are you a third year student, fourth year, or whatever? You have passed out or what? You graduated, not passed out actually. Yes, yes, Shubham, please. I'm not able to hear you. I'll just stop recording first because we have only less time for recording left. Then we can continue talking. Thank you very much for attending this lecture. I'll come to you, Shubham. Yes.